Today we've got a nice number theory problem which comes from an Austrian math Olympiad in the year 2003. And it has to do both with prime numbers and perfect squares. So our goal is to find all prime numbers, which we'll denote by p, such that 5 to the p plus 4p to the fourth is a perfect square. And generally, when you see this kind of mix of an exponential type object and a polynomial type object, you probably want to use the fact that an exponential object grows much more quickly than a polynomial object and produce some sort of inequality that takes over after a certain point. And that's exactly what we'll do as we solve this problem. Okay, so let's suppose we have an n where this expression is equal to n squared and see what we can say about p given that fact. Okay, so let's write that down. Let's take a natural number n such that we have 5 to the p plus 4p to the fourth equals that natural number squared. But now let's notice that this 4p to the fourth is also a perfect square. So if we subtract it over, we'll have a difference of squares, which will be actually pretty helpful. So let's write that down. We have n squared minus 4p to the fourth is equal to 5 to the p, like that. But what can we do from there? We can factor this difference of squares, which is on the left-hand side. We can factor it like n minus 2p squared times n plus 2p squared. And that's going to be equal to 5 to the p. But now we have the product of two things is equal to a power of a prime. Notice 5 is a prime. It's in fact a prime power of a prime, but that's kind of neither here nor there. But whenever you have a product of two things being a power of a prime, it means that each of these must be a power of that prime as well. So in other words, we have, I'll call these numbers k and l, which are natural numbers. Actually, they're not just natural numbers. Maybe they're non-negative integers, such that k plus l equals p. And you might say, well, where did that come from? That came from the fact that we're trying to write 5 to the p as 5 to the k times 5 to the l, and then we're using exponent rules to combine that together. And then finally, we have n minus 2p squared is equal to 5 to the k, and we have n plus 2p squared is equal to 5 to the l. Great. Again, using the fact that if the product of these is a power of 5, then each of these individually must be a power of 5. Okay, nice. Now, where would we want to go from here? Well, look, we can eliminate some things here if we try. In fact, we can eliminate this n, leaving us with just an equation involving primes, which is pretty powerful. And we can do that by taking this second equation and subtracting the first equation. So let's do that. So we're going to do equation, let's see, what did I say? 2 minus equation 1. And that'll give us the following expression or equation. So n minus n is 0. 2p squared minus negative 2p squared is 4p squared. And then over here on the right-hand side, we'll have 5 to the l minus 5 to the k. Next up, let's notice that this is almost always a multiple of 5 over here on the right-hand side. That's because we're taking the difference of two powers of 5. In fact, it's only not a multiple of 5 when k is equal to 0. I guess maybe while we're at it, let's point out that we immediately know that k is less than or equal to l. And that's because over here, actually we have a strict inequality. K is less than L because here we have n minus 2p squared and here we have n plus 2p squared. So 5 to the k is less than 5 to the L, which means k is less than L. Okay, so back to this. We know that this right-hand side is almost always a multiple of 5. So that means we can say this is congruent to 0 mod 5 in the special case, well, it's not really that much of a special case because it happens so often when k is not equal to 0. And that's because this guy right here is a multiple of 5, and this guy right here is a multiple of 5. We subtract them and we get a multiple of 5. But that leads us to say that p is congruent to 0 mod 5. In other words, p is a multiple of 5. But if p is a prime, which is a multiple of 5, then that means that p must be equal to 5. So that's our only possibility in this case when k is not equal to 0. Okay, so let's run through that and see exactly what perfect square we get. So we'll plug that over here. So we're going to have 5 to the 5 plus 4 times 5 to the 4. So maybe just like doing the big calculation would take a long time and not be super interesting. But let's notice that we can factor out a 5 to the 4 from this entire thing, leaving us with 5 to the 1 plus 4. Okay, but let's notice that 5 to the 4 is the same thing as 25 squared. And then 5 plus 4 is 9, which is 3 squared. So that makes this thing 75 squared. So that's most definitely a perfect square. So notice at this moment, we're actually not sure that we get a perfect square. We just see that it's possible to get a perfect square. Okay, nice. So, I mean, we've got a little bit of room left, but not quite enough to finish this thing off. So I'll just put here that next we'll look at the case when k is equal to 0. Let's see what setup that gives us. So if k is equal to 0, let's hone in on this equation. We have 4p squared equals 5 to the l, but that's got to be 5 to the p, given that k plus l equals p minus 1. Now maybe we'd like to rewrite this as 5 to the p minus 4p squared minus 1 equals 0. So we've got that sort of mixture of exponential and polynomial equation to solve. But like I said, exponential equations grow much faster than polynomial equations. So that leads us to kind of the intuition that this should be bigger than 0 for all p bigger than, I'll just put this box right here, this kind of box that we don't know anything about yet. And that's what we'll have to work towards on the next board and then check the remaining cases by hand. Okay, good. So let's maybe bring this to the top and then we'll finish it off. So far, we determined that we have a solution, and that's the solution when p is equal to 5. And in that case, our expression was equal to 75 squared. And then we determined also that if we had all other cases, then our p had to satisfy the following kind of exponential polynomial mixed equation here. So now we're going to finish this off by showing that this left-hand side is bigger than 0 after a certain point. And we're going to do this very loosely using kind of functions and calculus, maybe that are really easy to deal with. So let's maybe consider the following kind of nice exponential polynomial type equation, and that's going to be f of x equals e to the x minus 4x squared minus 1. So why e to the x instead of 5 to the x? Because it has a nicer derivative. Okay, so let's notice that 5 to the x minus 4x squared minus 1 is always strictly bigger than f of x. And that's because 5 is bigger than the number e. E is somewhere between 2 and 3. Okay, so let's also notice that f evaluated at 9, well, that's going to be equal to e to the 9 minus 4 times 81 minus 1. But that itself is strictly bigger than 2 to the 9 minus 325. So this number right here is 325, just by the way. But 2 to the 9 is 512, so this is 512 minus 325. And so it doesn't really matter what that is exactly, but 512 is clearly bigger than 325, so this is bigger than 0. Okay, so we have f of 9 is bigger than 0, and now what we want to build off of this is that f of x is bigger than 0 for all x bigger than or equal to 9. So let's say that f of x bigger than 0 for all x bigger than or equal to 9. But we can't immediately say that. So how will we do that? Well, we'll show that f is an increasing function. So if it's an increasing function and it's larger than 0 here, then it must be always larger than 0 for every point after here. So we'll do that by looking at the derivative. So notice f prime of x is equal to the derivative of e to the x is e to the x minus 8 times x. So we want that to be positive everywhere after 9. Well, let's find f prime of 9. So maybe through similar calculations, that's going to be bigger than 512 minus 16, which is bigger than 0. Okay, but maybe how could we show that this is bigger than 0 for all x bigger than 9? Well, I'm going to push to one more derivative. So let's take f double prime of x. And notice here we get e to the x minus 8. But let's notice if x is bigger than or equal to 9 here, that means that f double prime of x is strictly bigger than 2 to the 9 minus 8. So that's going to be, what, 512 minus 8, which is bigger than 0. And this works for all x bigger than 9 because this 8 is just a constant. Notice here we had 8 times x, so we would have had to do a little bit more work. Okay, so what does this tell us? So that means f double prime of x is bigger than 0 for all x bigger than or equal to 9. So that means f prime of x is increasing, but if f prime of x is increasing and it's positive here, that means that f prime of x is bigger than 0 for all x bigger than or equal to 9. But that means that f is increasing. But if f starts out being positive and keeps increasing, then it's always going to be positive. So that leads us up to this condition which we wanted to satisfy. So that means we have this. And since f of x is bigger than 0 for all x bigger than 9, that means that we have this inequality is only possible or this equality is only possible for p equal to 2, 3, or 7. We're going to leave off the case when it's equal to 5 because we already determined that that was a solution. Okay, and well, you might say, well, there are other numbers that are smaller than 9, but we don't really need to worry about them because those are the primes that are smaller than 9, other than 5, of course. But now, how could we finish this thing off? Well, I'll leave you guys to do it because there's not really much to it. What we would do is put each of these primes into our original expression and check that we do not get a perfect square. And so, since we don't get a perfect square when we plug each of those primes into our original expression, and by this argument, it says it's impossible to get a perfect square after that point, then that means this guy up here, p equals 5, is the only solution. And that's a good place to stop.